Hello, in this video I'd like to talk about non-standard models of Presburger arithmetic. As we add more and more expressiveness to our structures, the set of things that we can say, that we can talk about using first-order logical sentences increases. And remember that non-standard models have to agree with the standard model, have to agree in this case with the natural numbers, in all of those aspects. And so as we add more aspects that they have to agree on, that's going to restrict what sorts of non-standard models we can be looking at. In particular, the natural numbers with addition is more expressive than the natural numbers with just a notion of ordering. We can talk about the notion of ordering as just a first-order logical thing in Presburger arithmetic, but we can't talk about addition in the natural numbers as just a linear ordering. In a previous video, I demonstrated that all of the non-standard models of the natural numbers as a linear ordering looked like the natural numbers followed by some number of copies of the integers, where that number of copies could be actually any linear ordering. I call these structures Woozles because their formula is omega plus z times L. And so we expect when we look at non-standard models of Presburger arithmetic, well, because we can talk about ordering in Presburger arithmetic, we expect them necessarily to be non-standard models of the natural numbers as a linear ordering, but they're also going to have extra constraints on them. Perhaps only some types of Woozles work for non-standard models of Presburger arithmetic. And of course, these structures are also going to have a notion of addition, which our linear orderings did not have. In order to understand what these non-standard models look like, let's do the typical thing of constructing a new non-standard model of Presburger arithmetic using a compactness argument. Remember that in order to use a compactness argument, we need to construct a set of formulas such that any finite subset of those formulas is obviously satisfiable. And then compactness will tell us that the entire collection of formulas is satisfiable, and it will be satisfied by some non-standard model. So of course, in order to get that to work, we need to require that our non-standard model satisfy all of the true first-order logical sentences of Presburger arithmetic. From there, we want to add in some formulas that express that we have a new element. So let's add a new constant symbol c, and some formulas expressing that this element isn't any of the elements of the natural numbers. As before, any finite subset of this collection, S and T union together, is going to be satisfiable by the natural numbers with addition and C assigned to some appropriate value. Remember that if we're only taking a finite subset of these constraints on C, it's very easy to find a value of C that we aren't constraining it not to be. And so we can just assign the symbol C to be that number. I'll also leave it up to you if you want 0 and 1 to be symbols in our language, or if you just want them to be syntactic sugar. Remember that we have a formula in Presburger arithmetic that uniquely defines the number 0 and uniquely defines the number 1, and we can just replace these formulas here with those corresponding formulas that don't make reference to 0 or 1. Of course, now that we're working in Presburger arithmetic, we can add even more constraints onto C. For instance, we can specify whether C is even or odd by adding in either one of these two formulas. Regardless of which one we pick to toss into our set of constraints on C, it's still going to be possible when we're looking at a finite subset of our sentences that we need to satisfy to pick a C that satisfies those sentences, just by picking a sufficiently large number that's either even or odd, depending on whether we required C to be even or odd. Whether or not we specify it, our C is going to be required to be either even or odd. Within Presburger arithmetic, we can say that every number is either even or odd, and no numbers are both. Since this is something that we can express as a first-order logical sentence, it's actually in T. It's something that all of our non-standard models are going to have to satisfy. So let's pick some congruences for C modulo all natural numbers. Where each of these remainder terms is some number of ones added to themselves the appropriate number of times, depending on what remainders we'd like C to have. Of course, we can't just have an arbitrary set of remainders specified for C. We can express in the first-order logic of Presburger arithmetic that any number that's divisible by 4 is also divisible by 2, and any number that's congruent to 2 mod 4 is also divisible by 2. So if we tried to say that C was congruent to 2 mod 4 and also that C was congruent to 1 mod 2, the compactness argument would fail because we would have a set of two formulas that together aren't satisfiable, at least not with the addition of the formula in T that specifies that we can't have this situation. So we need to make some choices. We're of course free to pick whether we want this number to be congruent to 0 mod 2 or congruent to 1 mod 2. And then once we pick that, we have two choices for the congruences mod 4, which again we can pick freely. And then again we have two choices for the congruences mod 8. And so on and so forth. The choices that we make here for remainders modulo powers of 2 don't have to be satisfiable in their entirety. For instance, we're allowed to specify that our number is congruent to 1 mod 2 and 3 mod 4 and 7 mod 8, and in general, we could say that C is congruent to 2 to the n minus 1 modulo 2 to the n for every n. We can't find a natural number that has all of these congruences. -1 does, but it's not a natural number. It's not an element of this original structure. But that doesn't matter. What matters is that if we have a finite subset of this infinite set of constraints, that is satisfiable. A finite subset of this is only going to mention so many powers of 2, and just pick the largest power of 2. Let's say that the largest power of 2 that shows up is 8, and then we can pick C to be assigned to 7, and then it's going to have all of the congruences that we require it to have. So again, any finite subset of this infinite set of constraints is going to be satisfiable, and therefore we can use a compactness argument. In some sense, at each of the branches of this tree, we're picking out another binary digit of C, and we're not limited by the fact that the binary expansions of the natural numbers are all eventually zeros in high enough places. We're allowed to pick out an arbitrary infinite sequence of binary digits to represent the congruences for C modulo powers of 2. If you're familiar with the p-adic numbers, these are just the p-adic numbers where p is equal to 2. And a similar situation happens with all other powers of primes. We get to pick whatever remainders we want modulo powers of 3, as long as they're consistent with each other, as long as the remainders modulo 27 are consistent with the remainders modulo 9. Again, at each step we're essentially picking a new digit in base 3, but again, we're also not required for these choices to be entirely satisfiable. It only has to be the case that every finite subset of them is satisfiable. And so again, we get to pick an arbitrary branch through this infinite tree. And the remainders modulo powers of 2 are completely unrelated to the remainders modulo powers of 3. By the Chinese remainder theorem, if we specify a finite number of remainders modulo powers of 2 and a finite number of remainders modulo powers of 3, together we can find a number, an actual natural number, that satisfies all of those congruences, provided that the powers of 2 are consistent among each other and the powers of 3 are consistent among each other. But the powers of 2 and the powers of 3 are relatively prime, and so they don't influence each other at all. Of course, once we specify the remainders mod 2 and mod 3, that determines the remainders mod 6. And again, these are facts that the first-order logic of Presburger arithmetic is well aware of, that if a number is congruent to 0 mod 2 and 1 mod 3, then it has to be congruent to 4 mod 6. And similarly, specifying the congruences mod 4 and the congruences mod 3 together tell us the congruences mod 12. Once we've specified all of the congruences modulo powers of primes, we're done. We've specified all of the congruences. So again, we'll specify some consistent set of remainders for our number c. And again, we have tons of choices as to how to do that. And we'll put that infinite collection and call that R. One might ask, is this all that we can say about C? As we're constructing our non-standard model, it makes sense to try to constrain C as much as possible so that we have control over all the properties that C is going to satisfy when we construct this non-standard model around it. But remember that we showed that the only things that we can say with formulas with one free variable, things that we could say about some number, are that it belongs to some eventually periodic set. And by specifying all of the remainders of C, we specify all of the eventually periodic sets that it belongs to. Now I claim that every finite subset of T unioned with S unioned with R is satisfiable. And in particular, it's satisfiable by the natural numbers with addition and an appropriate assignment for C. Of course, this structure here is going to satisfy the set of all true first-order logical sentences of Presburger arithmetic. It's just Presburger arithmetic with a constant symbol added on. We only have in our finite subset here a finite number of values that C cannot be. And so eventually, if we look large enough, all of the numbers beyond a certain point are going to be allowable values for C, because the finite subset here is only going to constrain up to a certain point. And from R, we're also only going to get a finite set of constraints on C, a finite set of remainders modulo some finite set of moduli. So again, by the Chinese remainder theorem, there's going to be a value of C that makes this whole set of constraints work. As such, by compactness, the set T unioned with S unioned with R, the entire set of constraints, is also satisfiable. Again, not necessarily within Presburger arithmetic, and in fact the whole point was that we wanted to make sure that C didn't get assigned to be any natural number. But it is going to be satisfiable by some structure, by compactness. Let's call this structure M, and it's going to have its own notion of addition, but let's just call that notion addition. And it's going to have an assignment to the constant C. And again, compactness doesn't tell you much about the structure that you wind up getting unless you actually go into the details of the various proofs of compactness. So it could be the case that M calls its elements some completely random gibberish. But we can, of course, interpret what those elements are by determining how they behave with respect to the formulas that define the various natural numbers. Again, there's some formula in the first-order logic of Presburger arithmetic that uniquely defines the number 0. And so it's necessarily the case that in M, there's a unique element that satisfies that formula, that behaves exactly like the number 0, at least in terms of its first-order logical properties. So let's call this element 0. Similarly, we have a unique element that satisfies the property of being 1, and let's just call that element 1. And from there, we can construct more elements. We can construct 2, which is necessarily 1 plus 1, and we can construct 3, which is necessarily 1 plus 1 plus 1. M might have a completely different idea of what these elements are, but we can call them what they are and not get confused. Because M satisfies this entire set of constraints here, we know that C can't be any of these elements here. And so C is necessarily some infinite element. And as before, Presburger arithmetic is aware of our ability to add 1 and subtract 1, and still remain very far away from 0. It's also worth noting that there's a sentence in Presburger arithmetic that says that if we take an even number and add 1 to it, then we get an odd number. And in general, what that means is that once we know the remainders of a particular element, we know the remainders of that element plus 1, and that element plus 2, and that element minus 1. Determining the remainders for C determines the remainders for all of these elements here. But we're not done constructing our non-standard model. Presburger arithmetic is closed under addition. So that means in order to be logically indistinguishable from Presburger arithmetic, M also has to be closed under addition. And so that means that C plus C has to be an element of our non-standard model. This is going to be a very large element of our non-standard model, and in fact we can show that it can't be within some finite distance of C. We can write as a sentence in Presburger arithmetic that if a number is larger than 1 added to itself n times, then A plus B is at least n units away from A. And again, because this is a fact of Presburger arithmetic that can be expressed in first-order logic, it has to be true of M. And so, because C is larger than 1 added to itself n times for any concrete natural number n, then C plus C has to be at least n units away from C for any concrete number n. In other words, C plus C has to be infinitely far away from C. So this is going to create a new infinite piece that looks like the integers based around C plus C, containing, of course, C plus 1 and C plus C minus 1, and so on and so forth. Similarly, we're going to need to add in C plus C, that is 3 times C and 4 times C, and so on and so forth. And each of those elements is going to be infinitely far away from the previous one, and so is going to define a new chunk that looks like the integers within this Woozle. It's worth noting one of the tricky things about dealing with non-standard models of the natural numbers specifically is that you have to keep track of whether a number is an actual concrete natural number or an element of your non-standard model. Here, when I'm talking about elements like 2C or 3C or 4C, it's a concrete natural number times C. It's C added to itself some concrete natural number of times. So we don't necessarily have to have an element C times C. We could, but we're not required to, because Presburger arithmetic is not closed under multiplication. It doesn't even know what multiplication is. We also can't talk about remainders modulo C, because that would require adding x to itself C times within a formula. And again, that's not something that we can do, because C is not some concrete natural number. We can also divide. Either C or C plus 1 is even, and that means that there exists an x such that x plus x equals C or x plus x equals C plus 1. That x is going to be about C over 2, it's going to be C over 2 rounded, and it's going to be infinitely far away from both C and 0. It's going to be somewhere in here, and it's going to create a new piece that looks like the integers within our Woozle. If we have two actual natural numbers, then for every x there's going to exist a y which is approximately equal to p-qths of x. And this here is a true fact that we can express in the first-order logic of Presburger arithmetic. Again, we require p and q to be actual natural numbers and not elements of our non-standard model, because we need this px here to actually be x added to itself p times. And we actually need this ORing together to be a finite ORing. But once we do that, this here is a first-order logical sentence in the language of Presburger arithmetic, which is true of Presburger arithmetic. And so it has to be true of our non-standard model as well. In particular, this means that for our c, there's going to exist a y, which is approximately p-qths of c. I'm going to denote this element by this notation here. And for different rational numbers, p over q, we're going to get elements that are infinitely far apart from each other. So our non-standard model is going to look like the natural numbers followed by one copy of the integers for every one of these elements here. And we're going to have one of these elements for every rational number. And they're going to be ordered by those rational numbers. And so we get a very specific type of Woozle. It's a Woozle where we get one copy of the integers for every element of the rational numbers. It looks something like this. And even if we go on to expand our non-standard model further, because our non-standard model has to be closed under this approximate multiplying by a rational number operation, the L in our Woozle is going to have to be some sort of dense linear ordering without a largest or smallest element. The linear ordering structure of our non-standard model is going to have to be the natural numbers followed by a dense collection of copies of the integers with no largest copy of the integers and no smallest copy of the integers. One might ask, do we get to pick what the remainders of these new elements are? Of course, once we know what the remainders of these elements are, we know what the remainders of this element plus 1 and this element minus 1 and so on and so forth. In fact, the remainders of these new elements are determined by the remainders that we already picked at the very beginning for C. Suppose that we're interested in determining what 1/2 C rounded down mod 3 was, and we had already specified that C was congruent to 5 mod 6. Well, when we specified that C was congruent to 5 mod 6, we said that in the form C equals x added to itself 6 times plus 1 added to itself 5 times for some x. This 1/2 C element is necessarily then going to have to be x plus x plus x plus 1 plus 1 for that x, because we defined this element as the thing which, when added to itself and possibly adding another 1 onto it, gave us C, which this is what we said that C was equal to. So this 1/2 C rounded down necessarily has to be of this form. In other words, this element here is congruent. This is exactly how we expressed that this element here is congruent to 2 mod 3. This is very convenient. I was worried that we would have some choices here, and so I'd have to say something about like how to make those choices consistent with the choices that we had already made and what sets of choices we actually had. But no, we don't have any choices for the remainders of any of these elements here. They're all determined when we determine the remainders for C. So we've added a bunch of elements that we know have to be in the non-standard model by looking at the ways that Presburger arithmetic was closed under things that we could describe in first-order logic. Well, our non-standard model has to be closed under those things as well. It has to be closed under adding and subtracting 1, except we don't have to subtract 1 from 0, and it has to be closed under this multiply by a rational number and round down thing. But is that it? Is that all that our non-standard models have to be closed under? The answer is yes, and it's a little bit tricky to see. Essentially, the best way to show this is to prove that this structure here satisfies the axioms of Presburger arithmetic. Of course, we don't have to stop there. We can add in other new elements, and in fact, we can add in other new elements using a compactness argument. If we add in C and another new element D, don't forget to add in C plus D. If we're not interested in being creative about the remainders of C modulo various natural numbers, if we want to set all of those remainders to be 0, there's a very nice presentation of this non-standard model. M is just the natural numbers together with symbolic expressions of the form q times c plus z, where we're treating c really like just some sort of symbolic variable, like we do with I when we're talking about complex numbers, where q, the coefficient of c, is some positive rational number and z is an integer. And there's kind of a really intuitive way of adding together terms of this form. You just add together the coefficients of c and add together the integer terms. And of course, adding in a natural number is straightforward as well. That just affects the integer term. We can generalize this construction by replacing the positive rational numbers. I guess this should also be the positive rational numbers. By some structure, some set with a notion of addition to it, and that notion of addition has to be commutative and associative. It has to give rise to a total ordering where we can only subtract two numbers if one is larger than the other, so we don't have any negative numbers. I made a mistake saying that we could do this construction for any rational number. We can only do it for positive rational numbers. And this collection here should have a nice notion of multiplying by positive rational numbers. So for instance, the positive real numbers would work. Or various sets between the rational numbers and the real numbers. Or I've also seen this set here replaced by polynomials with, let's say, rational coefficients, where the leading coefficient is required to be positive. So the goal of this video series is to build up to a presentation of the non-standard models of the weak second-order theory of one successor. Or really, this is the same as asking what are the non-standard models of Buki arithmetic or the word logic, because they're all essentially expressively equivalent logics. And by this point in the series, I feel like I've built up enough tools and hopefully provided you with enough intuition to be able to make sense of the presentation. So starting with the next video, I'm going to be covering the content of my PhD thesis on the non-standard models of the weak second-order theory of one successor. I hope that you'll join me for that, and in the meantime, please leave any questions or comments that you have down below, and I hope to see you then.